request. Okay. So, hello everyone. Welcome to the IISc MSR Theory Seminar Series. This week we are delighted to have Professor Karthekeyan Chandrasekaran as our guest speaker. Professor Karthik is an associate professor at the Department of Industrial and Enterprise System Engineering in UIUC. He completed his PhD in Algorithms, Combinatorics and Optimization program at Georgia Institute of Technology. Before joining UIUC, he was a Simons postdoctoral research fellow at Harvard University. His research interests lie in the area of combinatorial optimization, integer programming, probabilistic methods, and randomization. He has regularly published in top-tier conferences like Soda, Fox, Scott, and so on. He has kindly agreed to give a two-part talk titled Partitioning over Submodular Structures. And today is the first talk, and the second talk will happen next week. So let's welcome Professor Karthik, and all yours.
Thanks, Ramesh. Right. So let me. Yeah, this talk is based on joint works with several co-authors, a lot of students, and as well as Chandrasekaran. All of them are from UIUC. The talk is an algorithmic talk. Please feel free to stop me if there are any questions, unmute yourself and raise questions. Since we have two parts, the goal is not to cover too much material, but make sure that the material that we cover is well understood. And pretty much this is an algorithmic talk. All algorithms that I'm going to describe are going to be simple 4-5 line algorithms. And then the correctness is going to be the non-trivial aspect of these algorithms. Right, and the goal will be to design polynomial-time algorithms. There will be no approximation, there will be no FPT, no hardness results. But if you're interested in talking about those, I'm happy to talk about those as well. But the main goal is to design polynomial-time algorithms. Right, so we'll be interested in submodular structures. Let me introduce submodular structures by focusing on hypergraphs. Hypergraph is specified by a vertex set and a collection of hyperedges. A hyperedge is a subset of vertices. So here is an example of a hypergraph. If every hyperedge has exactly two vertices, then the hypergraph is simply a graph. So hypergraphs generalize graphs. Hypergraphs will be a recurring theme throughout this talk and the next talk as well. We'll be interested in K partitions. A K partition is a partition of the vertex set into K non-empty parts. Non-emptiness will be an important constraint in all problems that we will consider. For example, here is a 3 partition of the vertex set V1, V2, V3. Next, how do we measure the quality of a K partition? We need some terminology. We will say that a hyperedge crosses a subset S if it intersects both S and the complement of S. S here is a subset of vertices. For example, the hyperedges crossing V1 are the red and green hyperedges. Hyperedges crossing V2 are green and orange. Hyperedges crossing V3 are red and orange. We will also say that a hyperedge crosses a K partition if it intersects at least two parts of the K partition. In this example, the hyperedges crossing this 3 partition V1, V2, V3 would be green, red, and orange. Now, with this terminology, there are several natural ways to measure the quality of a K partition. For example, we could measure the quality of a K partition by the number of hyperedges crossing the K partition. In this example, the number of hyperedges crossing this 3 partition V1, V2, V3 is 3. Or we could measure the quality of a K partition by the sum of the number of hyperedges crossing the 3 parts. In this example, the sum of the number of hyperedges crossing V1, this 3 partition would be 6. The number of hyperedges crossing V1 is 2, V2 is 2, and V3 is 2, so the sum is 6. Or we could measure the quality of the K partition by the max of the number of hyperedges crossing the K parts. In this example, the max of the number of hyperedges crossing the k parts is 2. Now, each of these measures leads to a natural objective in hypergraph K partition problems. In hypergraph K partition problems, we are given a hypergraph and a fixed constant K. Think of K as 2, 3, 4, 5, and so on. It is a fixed constant that is independent of the number of vertices in the hypergraph. The goal is to find a K partition so as to minimize the measure of interest. If the measure of interest is the number of hyperedges crossing the K parts, the problem is known as hypergraph KCut. If the measure of interest is the sum of the number of hyperedges crossing the K parts, the problem is known as min-sum hypergraph K partition. And if the measure of interest is the max of the number of hyperedges crossing the K parts, the problem is known as min-max hypergraph K partition.
Hey, Karthik?
Question, yeah.
So I was wondering whether, are you okay with questions in between? Sorry.
Yes, please, yes.
Yeah, so it's probably a basic question. In what sense is that measure a quality? So you mentioned quality in the quality of the partition in the previous slide. So in what sense would it be?
Quality
measure?
This is some way to measure the quality. These are, we want to quantify how good is a K partition. So one way to quantify this is to count either of these three possibilities and ask, can we minimize these?
So you want to minimize, okay.
Yeah, the goal is to minimize any of these three measures, and each one leads to a natural optimization problem, and the problems are hypergraph KCut, min-sum hypergraph K partition, and min-max hypergraph K partition.
Okay, thank you.
So what is the difference between 1 and 2? Is it a factor, like 2 difference, or this objective?
Good question. Good question. So if okay, so let me make the remarks right away. So firstly, if the input hypergraph is in fact a graph, then the second objective will be exactly twice the first objective. Okay, because each edge can cross exactly two parts. If it's crossing, then it can cross exactly two parts. So the second objective will be exactly twice the first objective if the input hypergraph is a graph. So graph KCut is equivalent to min-sum graph K partition if the input hypergraph is a graph.
For K uniform hypergraphs or something, maybe they are closely related, but otherwise they can be quite different.
No, even for uniform hypergraphs, 1 and 2 are not related. Because the issue is once you go to hyperedges, it can cross arbitrary number of parts. Think of a hyperedge which is of, let's say, size 5, and you are thinking of K equals 3, then it could cross 2 parts, it could cross 3 parts, and so on.
Thanks.
Right. So yeah, the first two problems, they coincide in, they're equivalent in graphs, but they're not equivalent in hypergraphs. In fact, all three objectives are not equivalent in hypergraphs. They lead to completely different solutions. That's the first remark. Second remark, min-max objective, the third objective here, min-max hypergraph K partition. In a sense, it aims to find a fair or equitable K partition where no part pays too much in cut value. So this is the connection to fairness, and because of this inherent connection to fairness, min-max objective has been studied in numerous combinatorial optimization problems, including job scheduling, min-degree spanning tree, discrepancy, etc. And the message from all these problems is that min-max objective is typically harder to solve or approximate than the min-sum objective. That's the situation for all those problems that I've listed there. But we will see a counterintuitive message for hypergraph K partition. Right. Any other questions on the problem definitions? Right. Our goal is to minimize these objectives. That's important. You can also think about maximizing, but that's going to be a different story altogether. But for our purpose, we are thinking about minimizing. Why do we care about these problems? Well, the first motivation for us is it comes from the fact that all these problems generalize global min-cut in graphs and hypergraphs. For example, if k equals 2, then all three problems are equivalent to global min-cut in hypergraphs. Okay, number of hyperedges crossing v1, v2, it's going to be, if k equals 2, then the second objective is exactly twice the first objective, and the third objective is exactly the first objective. Okay, so if k equals 2, then all three problems correspond to global min-cut in hypergraphs, which is poly-time solvable. So it is natural to ask whether these problems are poly-time solvable for larger constants k. What about k equals 3 and 4 and so on? Right, so that's one motivation. The second motivation for us to look into these problems comes from their connections to the much more general submodular K partition problem. In submodular K partition, we are given a submodular function via an evaluation oracle over a ground set V and a fixed constant k. Again, think of k as 2, 3, 4, and so on. It's a fixed constant that is independent of the size of the ground set. We would like to find a k partition of the ground set so as to minimize a natural measure of interest. If the measure of interest is the sum of the function values of the parts, the problem is known as min-sum submodular K partition. If the measure of interest is the max of the function values of the parts, the problem is known as min-max submodular K partition. Right, and if you've not seen submodular functions, here is the customary slide on submodular functions. A set function f is said to be submodular if for every pair of subsets A and B of the ground set, the sum of the function values on A and B is at least the sum of the function values on the intersection and the union. It turns out that the hypergraph cut function defined by this d of s, which is the number of hyperedges crossing the subset S of vertices, this is a submodular function over the ground set being the set of vertices. You can check the submodular inequality by simple counting, so this is not very difficult to see. So it turns out hypergraph cut function is a good example of a submodular function. And moreover, the hypergraph cut function is also symmetric. Symmetric says that the function value on a subset A is equal to the function value on the complement of A. The number of hyperedges crossing a subset S is equal to the number of hyperedges crossing the complement of S. So the hypergraph cut function is also symmetric. Now, from this observation, it should be immediately clear that min-sum hypergraph K partition is a special case of min-sum symmetric submodular K partition, because you can take the submodular function to be the cut function of the hypergraph. And similarly, min-max hypergraph K partition is a special case of min-max symmetric submodular K partition. Again, take the submodular function to be the cut function of the hypergraph. And moreover, hypergraph KCut is also a special case of min-sum submodular K partition. But the submodular function that you have to use to see this reduction it turns out to be an asymmetric submodular function. I won't describe this reduction. It is not very difficult, but it's a nice exercise to figure out this reduction. What is the asymmetric submodular function, which shows that hypergraph KCut is a special case of min-sum submodular K partition. And I'm happy to talk about this offline if you want to see this reduction. But any other questions so far?
Yeah, so one question is that so you assume this graph to be like undirected. Does this also generalize directed cuts, these functions, or?
Good. So you can also think about directed graphs and ask these submodular K partition questions. Yeah, so the directed min-sum directed graph K partition will be a special case of min-sum submodular K partition and so on.
How do you define direction in hyperedges? That's also not clear.
Good question. So there are directed hypergraphs. These are well studied. Here, every hyperedge has a single head and every other vertex in the hyperedge is a tail.
Okay.
So this is one way to define directed hypergraphs, and then you have to be careful with in degree function and out degree function. These you have to be careful with defining these, but yeah, these are also studied, right? Any other questions?
The quick question. So I'm guessing most of today's results hold for any fixed constant k, but if we hold k to be a small integer like k equal to 2 or something, are there any special results? Or,
k equals 2 is certainly the first case to think about, right? So k equals 2 corresponds to global min-cut in hypergraphs. All three problems coincide, and it corresponds to global min-cut in hypergraphs. And if for submodular 2 partition, again, k equals 2 is the more classic submodular minimization problem, which is polynomial-time solvable. So we'll get there. Yeah, k equals 2, we'll discuss k equals 2 shortly. Yeah, the main motivation is to solve the submodular K partition problem for larger constants K. And as a special case, hypergraph K partition problems are all these three problems are special cases of submodular K partition. Okay, let's quickly understand the challenges in solving these K partition problems. Let's talk about graph K partition for this. Here we are given a graph. We'll always talk about undirected graphs and a fixed constant K. Think of K as 2 or 3. We would like to find the K partition of the vertex set to minimize the measure of interest. Okay? If the measure of interest is the sum of the number of edges crossing the K parts, it's called min-sum graph K partition. And if the measure is the max of the number of edges crossing the K parts, the problem is min-max graph K partition. How would we solve this? What would be the first approach that we would try? Let's first think about k equals 2. When k equals 2, both these problems correspond to global min-cut in graphs. What is the first approach to solve global min-cut in graphs? Well, the first approach is to solve min-st cut for all pairs s and t and return the cheapest. Okay, that will be a global min-cut in graphs. Now, one could say, why not extend this approach to larger constants k? What about k equals 3 or 4? Why not do the same? That is, for each set of distinct terminal nodes, t1 through tk, we solve this subproblem, namely find a k partition of the vertex set such that the ith terminal is present in the ith part so as to minimize the measure of interest, namely the number of sum of the number of edges crossing the k parts. Solve this subproblem and return the cheapest of all of these. Now, if we could do this, then certainly this would solve min-sum graph K partition. But turns out the subproblem here is polytime only for k equals 2, and it becomes NP hard even for k equals 3 and so on. So this subproblem is called, I'll call this as min-sum multi-way cut. This is NP hard even for k equals 3. So this first approach, which worked for global min-cut in graphs, it already fails for even k equals 3, min-sum graph 3 partition. And the situation is same for min-max. The subproblem for min-max would be min-max multi-way cut. Min-max multi-way cut is NP hard for k equals 4 and so on. So the first approach, which worked for global min-cut, already fails for k equals 3 and 4 and 5 and so on. Questions on this? Right, so graph 3 partition is already non-trivial. Forget about submodular functions, even graph 3 partition is already non-trivial. That's what I want you to observe from this slide. But let's go back to submodular K partition, and let me tell you what is known about submodular K partition. For arbitrary question, yeah.
So in the you earlier talked, the min-max question is normally harder than the min-sum question. But here, for example, you are saying for k equal to 3, it's NP hard min-sum. But for k equal to 3, maybe the min-max is not NP hard, or what is known for k equal to 3?
Yeah, for min-max multi-way cut for k equals 3, the complexity status is open. We don't know if it is poly-time or NP hard. Very likely that it is NP hard, but we just don't know the status of this.
Yeah, thanks.
Okay. Yeah, let's go back to submodular K partition. What is known about these problems? When k equals 2, submodular 2 partition, min-sum submodular 2 partition is poly-time. This is like solving global min-cut. You want to partition the ground set into 2 non-empty parts so as to minimize the sum of the function values of the 2 parts. You can solve this provided you can solve min-st cut for submodular functions. Okay, min-st cut for submodular functions. What is this problem? You're given a subset S and T of the ground set. You would like to find a subset A that contains S and is disjoint from T so as to minimize the sum of the function values on A and the complement of A. Okay, if you can solve min-st cut for submodular functions, then you can also solve global min-cut, that is min-sum submodular 2 partition. Turns out min-st cut for submodular functions, this is the classic submodular minimization problem, which is polynomial-time. So you can solve min-sum submodular 2 partition. This is the folklore reduction to min-st cut. But there are also ordering-based algorithms to solve min-sum submodular 2 partition, which is due to Quiran. Okay. So this is the status for min-sum submodular 2 partition. What about min-max submodular 2 partition? What about, so min-max submodular 2 partition? What do you think? Is this poly-time or for k equals 2? Min-max submodular 2 partition.
NP hard.
Yeah, this is NP hard even for k equals 2. The reason is because partitioning a given set of integers into 2 non-empty parts so as to minimize the maximum sum of the values of the 2 parts is already NP hard. Integer 2 partition is already NP hard. Essentially, min-max modular 2 partition is already NP hard. Forget about min-max submodular 2 partition. So this is already NP hard. So there is no hope here. But let's talk about symmetric submodular functions, which is a special case of submodular functions. So min-sum symmetric submodular 2 partition is also poly-time. But min-max symmetric submodular 2 partition, well, if you think about min-max symmetric submodular 2 partition, if the function is symmetric, then this is in fact a special case of min-sum submodular 2 partition, right? Because if the function is symmetric, the function value on A is equal to the function value on the complement of A. So this is a special case of min-sum submodular 2 partition. So this is polynomial time for k equals 2. Questions on this? Okay. Good. So the natural question we want to think about here is, well, we know that it's poly-time for k equals 2. What about larger constants k? The min-sum submodular k partition. And similarly, what about min-max symmetric submodular k partition for larger constants k? Ideally, we would like to be able to say that these are also poly-time. We didn't know the status. We did not know the status of these 2 problems until about 4 or 5 years ago. But if we don't know the status, then it's good to think about some special cases. I'll talk about 3 special cases of submodular functions, namely graph cut function, hypergraph cut function, and hypergraph KCut. And recall that hypergraph KCut is a special case of min-sum submodular K partition. There is no min-max counterpart to it. So I'm going to put a dash in the min-max column for hypergraph KCut. Right. So for these special cases, let's first talk about graph cut function min sum graph K partition. We already saw that min sum graph 3 partition is already non-trivial. You need some new ideas to solve this. Nevertheless, this has been done before, back in '94, in the early '90s. Goldschmidt and Hochbaum showed that min sum graph K partition is polynomial time for every fixed K. And the min-max graph K partition is also polynomial time for every fixed K. This follows via results due to Karger and Stein. Right. For hypergraph cut function min sum hypergraph 2 partition, this is a special case of submodular min sum submodular 2 partition. So this is polynomial time for K equals 2. So all these three cells are special cases of submodular function. So we get these results for K equals 2. So given this was the status until a few years ago. So the natural questions are to understand, are to first answer min sum submodular K partition and min max symmetric submodular K partition for larger constants K. But if we don't know how to bring this into polytime, it is good to think of these special cases. What about min sum submodular K partition for larger constants K? Symmetric submodular K partition for larger constants K. In fact, this min sum symmetric submodular K partition has a bit of notorious history. This was claimed to be polytime in '98 by Querran, but it was subsequently retracted, so we don't know the complexity of min sum symmetric submodular K partition for larger constants K. And if we don't know that, then it's good to think about these special cases, min sum hypergraph K partition for larger constants K, and min max hypergraph K partition for larger constants K, which was in fact raised as an open problem by Lawler in '73, and hypergraph KCut for larger constants K. The hope is understanding these special cases will help us get to the first two problems, min sum submodular K partition and min max symmetric submodular K partition. Right, so this is how I started looking into these problems. Questions on these?
So one question, so this monotone submodular function, are they studied in this context or anything better known for those classes?
So yeah, we don't know polytime solvability for monotone functions either. So that's the status for even for monotone. Approximability, I don't think anything better is known. Monotone submodular functions are more interesting from the perspective of maximization problems than minimization problems. So there we think about approximations when we want to maximize these measures. Minimizing, yeah, we don't know polytime for monotone either.
Okay, thanks.
Let's get to the results. The first result that we managed to show is that hypergraph KCut is in fact solvable in polynomial time for every fixed K. Note that this is a special case of min sum submodular K partition. So the first algorithm which we gave was a randomized algorithm, and I'll discuss that. Subsequently, we gave a deterministic algorithm, polynomial time algorithm for hypergraph KCut, which inspired us to see a polynomial time algorithm for min-max symmetric submodular K partition. We were able to bring that into polytime, which immediately implies a polytime algorithm for min-max hypergraph K partition, thus resolving the open question posed by Lawler. Right, so these are the results that we have currently. Note that counterintuitive to what has happened in the literature. We know that min-max symmetric submodular K partition is polytime for every fixed K, but we still do not know if min-sum symmetric submodular K partition is polytime for every fixed constant K. This is sort of a strange situation than most problems in literature when you compare min-sum versus min-max. Right. So these are the results that I want to talk about today and the next talk. We have some more results. I'll come to them maybe towards the end. So the rest of the talk will be about this first result, polynomial-time algorithm for hypergraph KCut. This was a randomized algorithm. I'll talk about this, and then next talk I'll talk about the deterministic algorithm for hypergraph KCut and the deterministic algorithm for min-max symmetric submodular K partition. Right. So this is the plan for the rest of the talk. Will focus. The rest of the talk will be purely about hypergraph KCut. Any questions on results?
So quick question. What possibly quite general question, what advantages does a hypergraph give over symmetric submodular functions that it gets easier?
Yeah, so hypergraphs, there are some difficulties compared to graphs. So yeah, the main advantage, even if you think about graphs, so we'll get to that. So hypergraph KCut, why is this polytime? We'll talk about that in the randomized algorithm, but you will see. Yeah, I'll get to that. Yeah, we'll see that. We'll see the randomized algorithm, and one might wonder why doesn't this generalize to submodular functions? And you will see, as soon as you see the randomized algorithm, you'll see why it doesn't generalize. Yeah, if we don't see it, we'll come back to that question in the end. Yeah.
Yeah. Thank you.
Right, so the rest of the talk will be about hypergraph KCut. I'll tell you the randomized polynomial-time algorithm for hypergraph KCut. What is the problem? Again, we are given a hypergraph and a fixed constant K. We would like to find a K partition of the vertex set with minimum number of crossing hyperedges. Now, it is helpful so initially for the randomized algorithm, instead of thinking about it as a partitioning problem, it is equivalent to finding a minimum number of hyperedges to remove so that the resulting hypergraph has at least K components. These two problems are equivalent. Finding a K partition with minimum number of crossing hyperedges is so whatever you find such a K partition, look at the crossing hyperedges, you remove those, then the remaining will have at least K components. So these two problems are equivalent, and it is helpful to think about it as a deletion problem. That is, find a minimum number of hyperedges to delete so that the remaining hypergraph has at least K components. So this is the version that we will think about to design this randomized algorithm for hypergraph KCut. The main technique that we introduce here to solve this problem is non-uniform random contraction. To describe this technique, let's think about the special case of K equals 2. How do we solve the hypergraph 2-cut problem? So this is K equals 2 corresponds to global min-cut in graph. So I'll spend a good chunk of the remaining time telling you how to solve global min-cut in hypergraphs via this random contraction approach. So the good chunk will be about how to solve global min-cut in hypergraphs, that is this which corresponds to hypergraph 2-cut. And then once we realize how to solve this via random contractions, the generalization to larger constants K, I'll tell you the generalization, how to generalize the algorithm to larger constants K. So that's going to be the plan. So let's first think about how to solve global min-cut in hypergraphs. Here we are given a hypergraph. We would like to find a minimum number of hyperedges to remove so that the resulting hypergraph has at least 2 components. This is our problem. And we want to solve this via random contraction. So we want to solve global min-cut in hypergraphs via random contractions. If you think about global min-cut in graphs, one way to solve this is via the uniform random contraction algorithm due to Karger. How did that go? You repeatedly contract edges until you pick a uniform random edge, contract and repeat until the graph has only two vertices, at which point you return all edges between those two vertices. Okay? And this will be a global min-cut with large enough probability. This was Karger's uniform random contraction algorithm. Now, why not try to do the same for hypergraphs? That would be the first approach that you would think about. So let's first define hyperedge contractions. So graph edge contractions is naturally defined. How do we define the hyperedge contraction operation? This is the natural operation that you would think of. So suppose this is our hypergraph and I want to contract this purple hyperedge E. Then I will introduce a new vertex. And for every other hyperedge that intersects E, I'm going to include this new vertex into that hyperedge. And I will delete all hyperedges present in E, and I will delete self-loops. So E is a self-loop here, so I'll delete E itself. And I'll denote the hypergraph obtained after this process as G/E. This is the hypergraph obtained by contracting E. So this is the natural notion of hyperedge contraction that you would think of in hypergraphs, going from graphs to hypergraphs. Any questions on this? Okay, so with this definition of contractions, it's very tempting to just run Karger's uniform random contraction algorithm, right? So why not take a uniform random hyperedge, contract and repeat until the hypergraph has only two vertices, at which point you return all hyperedges between those two vertices. Why not try to do the same? Well, here is a simple example where this fails drastically. Look at this hypergraph. It has only one hyperedge, namely this hyperedge which contains all vertices. Okay, I'll call this hyperedge as a spanning hyperedge because it contains all vertices. It contains more than two vertices, so if you try that approach, you will contract this hyperedge, which will leave you with only one vertex. So you don't get two vertices, you don't have a cut to report. So this first approach which you would try, namely pick a uniform random hyperedge and contract, this doesn't even give you a cut, let alone a min cut. It doesn't even give you a cut. So this is a serious problem. You can't simply run Karger's uniform random contraction. And we played around with a few more examples, and the message from these examples is that you should not be contracting according to the uniform distribution. Okay. So our key insight is to dampen the probability of picking large hyperedges. So this spanning hyperedge is a large hyperedge. You don't want to pick large hyperedges with the same probability as small hyperedges. In a sense, picking large hyperedges with the same probability as small hyperedges leads to you have a higher chance of making a mistake, contracting large hyperedges. So you want to dampen the probability of picking large hyperedges. This is the approach. So how do we dampen? So the first thing you would try is, why not pick hyperedges with probability that is inversely proportional to the size of the hyperedge? Or why not inversely proportional to the squared size of the hyperedge, or cubed size of the hyperedge, and so on. So you could try these things. What we give is a clean way to dampen. So we don't do any of these. We give a different way to dampen. Okay. So here is the dampening factor. We define the dampening factor of a hyperedge E, alpha E. I'll denote this as alpha E. This is the probability of a uniform random vertex not being in the hyperedge. Note that this can be computed explicitly. This is the number of vertices minus the size of the hyperedge divided by the number of vertices. Now, with this definition of the dampening factor, here is our algorithm for global min-cut in hypergraphs. Given the hypergraph input hypergraph G, we compute these dampening factors. Now, what does it mean if the dampening factor of a hyperedge E to be 0? It means that the hyperedge E is a spanning hyperedge. It has to contain all vertices, which means it crosses every cut. In particular, it crosses the min-cut. And if all dampening factors are 0, then all hyperedges are spanning. So in fact, you should be returning all hyperedges. This is the correct thing to do. Okay, so this is the first step. If not, then we pick a hyperedge E with probability proportional to this dampening factor, contract this hyperedge, recompute the dampening factors, and repeat until the hypergraph has at most 4 vertices. And if the hypergraph has at most 4 vertices, then it is a constant sized hypergraph. You can return a minimum cut in this constant sized hypergraph by brute force. So this is our algorithm for global min-cut in hypergraphs. And the rest of the time, I'm going to tell you why this algorithm is, it succeeds with large enough probability. We will analyze this algorithm. But before we analyze the algorithm, few remarks about the dampening factor and the algorithm. Let's look at the dampening factor, alpha E. Note that this is inversely, in a sense, it is inversely proportional to the size of the hyperedge, because larger the size of the hyperedge, smaller is the dampening factor. So smaller is the probability of picking the hyperedge. So in a sense, this is doing what we would like. Second remark, if the input hypergraph is a graph, then what does this algorithm do? If the input hypergraph is a graph, then all hyperedges E have size 2, which means all dampening factors alpha E will be the same, which means this dampened sampling will in fact be a uniform random sampling. So if the input hypergraph is in fact a graph, then the algorithm is exactly Karger's uniform random contraction algorithm. So this is a generalization of Karger's uniform random contraction algorithm.
So one question. So here, what is special about 4? If we use any constant, then you can solve it by brute force. So why not 3 or some other constant, for example? Yeah,
so 4, I need this for some inductive step to work. Karger, you can stop at 2, whereas here I need it to be 4 for some inductive step to work.
I see.
So with a uniform hypergraph, this would again be a uniform sampling?
No, not really, right? If you start with a uniform hypergraph, after you contract a hyperedge, your hypergraph may not be uniform anymore.
Yeah, right.
Yeah, so we believed that uniform case would be good to understand, but turned out that once you get into contractions, there is nothing helpful about uniform hypergraph. Okay, let's analyze the correctness probability. It should be clear that running time is polynomial time, because you can compute these dampening factors alpha E's efficiently, and then you can sample efficiently, and contraction is poly time. Each contraction reduces the number of vertices, so overall the algorithm is poly time. This is easy to see. What about the correctness probability of this algorithm? Okay, so let's analyze the correctness probability. I'll show you the full analysis. We have about 15 minutes. I'll show you the entire analysis. This fits into 2 slides. It's not very difficult. Okay, the first observation here is if you pick a hyperedge E which is not in a min-cut set C star. I'll denote C star as a min-cut set, the set of hyperedges crossing a min-cut. If you pick a hyperedge E which is not in the min-cut set, and you contract this hyperedge E, then you're not going to disrupt the min-cut set. So C star will still be a min-cut set in the contracted hypergraph. This is the first observation. Let's analyze the success probability of this algorithm. I've moved the algorithm to the top left and the dampening factor to the top right. So let's look at a n-vertex hypergraph. Let's define Qn to be the minimum probability of the algorithm returning a particular min-cut set C star on the input hypergraph G. Let's take the minimum of all these. We will show that this Qn is at least 1 over n choose 2 by induction on n. And this would be good because this tells you that the probability that the algorithm returns a particular min-cut set on an input hypergraph G is at least 1 over n squared. So you can repeat this n squared log n times and take the best, you will get a min-cut. So it's enough to show that Qn is at least 1 over n choose 2. Right, so let's look at the n-vertex hypergraph G and the min-cut set C star on which achieves the minimum. This Qn is achieved. Now the probability that the algorithm returns C star on input G is the sum over all hyperedges which are not in C star of the probability that the algorithm contracts such a hyperedge E and returns C star on the contracted hypergraph as input. Now, the probability of contracting the hyperedge E is this PE, which is coming from the algorithm here. And the probability that the algorithm returns C star on input G contract E, note that when you contract E, the number of vertices in the graph, in the contracted hypergraph, will be n minus the size of E plus 1. And by induction, the probability that the algorithm returns C star on G contract E is at least Qn minus size of E plus 1. This is by definition of the Qn. So what we have showed is that Qn is at least the sum over all hyperedges which are not in the min-cut set C star of PE times Qn minus size of E plus 1. Now, let's substitute this PE. The probability of picking the hyperedge E is the dampening factor of the hyperedge divided by the normalizing factor. Now, let's move the normalizing factor outside the first sum and look at this alpha E times Qn minus size of E plus 1. What is alpha E? Alpha E by definition is n minus the size of E divided by n. And Qn minus size of E plus 1, well, the size of E is at least 2, so n minus size of E plus 1 is at most n minus 1. So by induction hypothesis, Qn minus size of E plus 1 is at least 1 over n minus size of E plus 1, choose 2. Here is where we are using induction hypothesis. Now simplify this expression, you get 2 over n times n minus size of E plus 1. Now size of E is at least 2. Which means n minus size of E plus 1 is at most n minus 1, which means this is at least 1 over n choose 2. What we've shown is each of the terms in this sum is at least 1 over n choose 2. So the number of terms here is the number of hyperedges which are not in the min-cut set C star. So substituting this lower bound, you get Qn is at least 1 over n choose 2 times the number of hyperedges not in the min-cut set C star divided by the normalizing factor. Questions so far? Okay. I promised that Qn is going to be at least 1 over n choose 2. So what remains to show is the number of hyperedges which are not in the min-cut set C star divided by the sum of the dampening factors should be at least 1. Okay, this is what we need to show to finish the rest of the proof. So let's show this. Okay. So we want to show that this ratio is at least 1. Let's rewrite this ratio. Move you move the denominator to the right hand side and rewrite this rewrite what we need to show. What we need to show is an upper bound on the size of the min-cut set C star. Here C star denotes the set of hyperedges crossing a min-cut. So we just have to show an upper bound on the size of the min cut set C star. Well, how do we show an upper bound on a minimization problem? We come up with a feasible solution, right? The value of that feasible solution will be an upper bound. So what is the natural feasible solution? Well, look at a vertex, look at all hyperedges incident to that vertex. I'll denote the hyperedges which are incident to that vertex as delta V. Now this is a cut, whereas C star is a min cut. So the size of C star should be at most the number of hyperedges incident to a vertex V. And this should hold true for all vertices V. Which means if I pick a uniform random vertex V and look at the number of hyperedges incident to that vertex, the expected value of the number of hyperedges incident to a uniform random vertex V should be at least the size of the min cut set. Now, the number of hyperedges incident to a vertex V, I can write it as the sum over all hyperedges F of the indicator function of the vertex V being in the hyperedge. Now, by linearity of expectation, this is the sum over all hyperedges F of the probability of a uniform random vertex being in the hyperedge, which is 1 minus the probability of a uniform random vertex not being in the hyperedge. But the probability of a uniform random vertex not being in the hyperedge is exactly the dampening factor of the hyperedge. Okay, that's how we define the dampening factor of a hyperedge. And this sum is exactly the number of hyperedges minus the sum of the dampening factor. So that is exactly that's the upper bound that we wanted to show on the min cut set C star. And that proves that the ratio is at least 1, and which in turn proves that Qn is at least 1 over n choose 2. Questions on the analysis?
So where do we need that k is a fixed constant?
No, we didn't use, this is about global min cut, right? This is about k equals 2. We are only talking about how to solve global min cut. We moved away from the hypergraph KCut problem. First you have to solve k equals 2. How do we solve k equals 2? This is one way to solve this. What was not known in the literature was this clean distribution and this clean analysis. This was somehow not known in the literature for hypergraph global min cut. Right. So to answer questions,
Sorry, go ahead.
No, I was going to go back to answer Arindam's question. Why do I need to stop at 4 vertices instead of 2? Turns out this step here, this step to here, this inequality holds only if n is at least 4, and that is why I had to do that stop only at least 4 vertices, which is sort of minor, but this is the only catch here. Maybe this can be adjusted, but
I have a question. So earlier you mentioned something like, so I didn't get it there. So what is that? That the general calculating all cuts will not work. What was that about? Like similar to global ST min cut, we can't compute all ST cuts. That was for k greater than 3 case. What was that?
Yeah, that's only for k at least 3. So in fact, you can solve global min cut in hypergraphs by solving min ST cut in hypergraphs, but that is not helpful for k equals 3. So that approach is not a viable angle for k equals 3.
I see. Okay. But this problem for k equals to 2 can be computed via that way, computing algorithm.
Yeah, it can be solved via that approach.
Okay.
Okay, so what we've shown is that this 4-line algorithm, it solves global min cut with probability at least 1 over n choose 2. It returns any fixed min cut set in an n vertex hypergraph with probability at least 1 over n choose 2. So repeating this order n squared log n times and returning the best will in fact return a min cut set with high probability. And structural consequence of this of the first result, the analysis, is that the number of distinct min-cut sets in a n-vertex hypergraph is at most n choose 2. Right. Okay, so this is about hypergraph min-cut, that is k equals 2. Now let's talk about k at least 2, k larger than 2. The algorithm and the dampening factor that I've written here are for k equals 2. Turns out for larger constants k, you need to change the dampening factor. The algorithm is still going to be the same, but the dampening factor for a hyperedge E, we define this to be the probability of a uniform random subset of k minus 1 vertices being disjoint from the hyperedge. And this can be computed explicitly. It's the ratio of n minus size of E choose k minus 1 divided by n choose k minus 1. But recall that k is a fixed constant. So these binomial expressions can be computed in polytime. And the algorithm is almost the same. Instead of stopping at 4 vertices, you're going to stop at 4 times k minus 1 vertices. And instead of returning a min-cut set, once you have 4 times k minus 1 vertices, you have constant number of vertices. You want a k-cut set, so you brute force to find a min k-cut set. And that's how we generalize it to larger constants k. I showed you the entry analysis for k equals 2. For larger constants k, the analysis is along the same lines. You just have to be careful with manipulating the binomial expressions, and the analysis is along the same lines. And we can show that this algorithm returns any fixed min k-cut set in an n-vertex hypergraph with probability at least 1 over n choose 2 times k minus 1. So repeating this n raised to 2 times k minus 1 log n times and returning the best will give a min k-cut set with high probability. Recall that k is a fixed constant, so n raised to 2k minus 2 is polytime. And we get this structural result as well. The number of distinct minimum k-cut sets in an n-vertex hypergraph is order n raised to 2 times k minus 1. Right. Questions on this?
Hi. So, is there a lower bound which can be shown on the runtime for some k?
Is there a lower bound on the runtime for k? I believe there is an n to the k lower bound for graphs. One cannot expect anything better than n to the k for graphs, and turns out this algorithm, when specialized to graphs, is the Karger-Stein's algorithm for graph KCut, and that algorithm's analysis has been improved recently to show that it runs in time n to the k.
So can you sort of do that here as well?
We don't know the answer to that. Good question. We have been thinking about it. I don't know the answer to that.
Thanks.
I have one question. So you talked about this unweighted case and uniform sampling, but in the weighted case also, Karger-Stein works when you sample with probability proportional to the weights or something. So in this case, the dampening factor can change. Yeah.
Good. So throughout, so when I defined the problem, okay, I don't want to go back all the way, but yeah, even for global min-cut, I defined the problem as deleting the smallest number of hyperedges to disconnect the hypergraph, right? If you have weights on the hyperedges, you can run the same algorithm. You will multiply the dampening factor alpha E by the weight of the hyperedge E. So alpha E gets replaced by alpha E times the weight of the hyperedge. That's your new dampening factor. And then you can run the same algorithm. So in a sense, you can think about, if you have weights, then you can think of those as multiple copies and run the same algorithm, and the analysis goes through. So you just have to multiply these dampening factors by the weights. So yeah, everything that I mentioned works for the weighted case. I just wanted to keep things simple so that we can do the analysis.
Thanks.
Right. So this is all I wanted to tell you today. The randomized algorithm for hypergraph KCut. Next talk we will talk about how to make it deterministic. Maybe a few questions to maybe think about and also address. Why doesn't this work for min sum submodular K partition? Why doesn't this randomized algorithm work for min sum submodular K partition? Anybody wants to answer this already? Well, why doesn't this work for min sum submodular 2 partition? Why doesn't this work for global min cut and for submodular functions? Well, in the algorithm, we did not use anything about submodularity. If you think about the algorithm, we used the fact that hyperedges can be contracted. Whereas for submodular functions, it's a function defined over the ground set which corresponds to vertices. You don't have this nice hyperedge structure, so there is no notion of contraction of hyperedges that you can define for submodular functions. So that's the big bottleneck which completely makes this randomized algorithm, it doesn't generalize to submodular functions, and the whole reason why we set out to solve hypergraph KCut, it miserably fails. It doesn't generalize to submodular functions. So in a sense, this approach itself is flawed. It's not going to work for submodular functions. Okay, so does that make sense? Does it answer the question from the beginning?
Yes.
Yeah. So in a sense, this was, but our goal was to bring it into poly-time, and this was our first result. And now that we brought it into poly-time, the next question was, okay, it doesn't generalize. So can we get a deterministic polynomial-time algorithm for hypergraph KCut? Okay, that's the, and if you think about it, there is no way to de-randomize Karger's random contraction algorithm. There are deterministic algorithms for global min cut, but I wouldn't call those as de-randomization of Karger's uniform random contraction algorithm. To me, de-randomization, you have to identify which edge to contract. If you can do that, then that in a deterministic fashion, then okay, that's de-randomization. But we don't know how to do that even for Karger's uniform random contraction algorithm for graphs. Okay, so this random contraction approach, we don't know how to make it deterministic in the way of getting by doing a de-randomization. Okay, so we need completely new techniques for deterministic algorithm for hypergraph KCut, and that's the next. That's what I'll talk about in the next talk. Okay. All right, I'll stop here for today. Thank you very much for your attention, and I'm happy to hang around and take any questions or go through the analysis if you want to see it again.
Yeah, I had a question regarding the analysis. There was one step where you used uniform random over the vertices. Maybe if you could go over that just once again.
Let's go back to the analysis. So I'm happy to do this again. The analysis is a bit subtle, and a different way of thinking about it doesn't work. So I'm also happy to point out why different ways don't work. So let's look at this Qn. So Qn is so fix the n vertex hypergraph G and a min cut set C star, which achieves the minimum for Qn, this minimum. Now, the probability that the algorithm returns C star on G is the sum over all hyperedges which are not in C star, probability of algorithm contracting E and returning C star on the contracted hypergraph. This is P is the probability of choosing hyperedge E to contract, and once you contract, the size of the hypergraphs G contract E is n minus size of E plus 1. And size of E is at least 2. All hyperedges have size at least 2. So n minus size of E plus 1 is at most n minus 1. So by induction, the probability that the algorithm returns C star on G contract E is at least the minimum probability of the algorithm returning min cut set on input hypergraph of size n minus size of e plus 1. Okay, so this is by induction. So we've shown that Qn is at least this lower bound. Now substitute the PE. This is the dampening factor divided by the sum of all dampening factors. Move the sum of all dampening factors outside. The dampening factor of the hyperedge E is n minus size of E divided by n. And Qn minus size of E plus 1 by induction is at least 1 over n minus size of E plus 1 choose 2. Now 1 over n minus size of E plus 1 choose 2, you expand that out and cancel n minus size of E, you get this expression. Size of E is at least 2, so n minus size of E plus 1 is at most n minus 1, so this is at least 1 over n choose 2. Now plug this lower bound, so each term in the sum on the left side is at least 1 over n choose 2. The number of terms is the number of hyperedges not in C star, divide, and you have the normalizing factor in the denominator. Now Qn was supposed, we wanted it to be at least 1 over n choose 2, so we need to show that this ratio is at least 1. Now this ratio showing that it's at least 1, now rewrite this what we need to show, it amounts to showing an upper bound on C star. Okay, multiply both left hand side and right hand side by the sum of all dampening factors, and then move C star to the other side and the sum of all dampening factors to the other side, you get, this is what we want to show. So we want to show an upper bound on the size of the min cut set C star. Okay. To show an upper bound on a minimization problem, we show a feasible solution. Its value will be an upper bound on the value of the minimization problem. So what is a feasible solution? Well, the natural feasible solution is look at a vertex V, look at all hyperedges incident to that vertex V. I'll call these as delta V. These are all hyperedges which contain that vertex V. Now, if you delete all these hyperedges, then you've disconnected the hypergraph. So this is a feasible cut. Whereas C star is a min cut, so the size of a min cut should be at most the size of a feasible cut, and this should hold for every vertex V. Which means if you pick a uniform random vertex and look at the size of the number of edge, the size of the incident hyperedges to vertex V, then this is a lower bound. So the expected size of the degree of V, the expected degree of V is a lower bound on the size of a min cut.
Yeah.
Now,
So here's my question. Question was, why not use the max degree or something?
Why not use the max degree? So the point is we want to, certainly that's a, sorry, max degree is an upper bound, but you want a tighter upper bound. Min degree is also an upper bound, right?
Right.
Right. So you could have used min degree, except yeah. So we don't. So the bottom right, we know this for all V, this upper bound. But look at what we need to show. We need to arrive at this. The upper bound needs to be the size of the number of hyperedges minus the sum of the dampening factors. And how do we do this? One way to do this is an averaging argument. Yeah, you could use the min degree, but the min degree is at most the, how do we bound the min degree? Min degree is at most the expected degree. So this is why I used expected degree.
That answers my question. Thank you.
Yeah, the expected degree, and then you massage this expression and you get the clean upper bound here. Yeah, the reason I wanted to write this out explicitly is to point out the inequality is coming only because of, only in that first step. After that, the rest of it is all equation.
Okay, so do we have any other questions?
Yeah, so what about approximation for non-constant k, let's say?
So you want to talk about approximations. Let me, I do have a slide for that. The situation is sort of bleak there. Let me share this. Okay, so if k is not constant, can you see these slides again?
Yes.
Okay, so if k is arbitrary, so here's where so the top first line I've said, if k is arbitrary, if k is part of input, then here is the situation. Even for min-sum graph k partition, this is already NP hard. It's a reduction from independent set, so it already becomes NP hard, which in turn implies that all these problems are NP hard. And you can get a two approximation via Gomori-Hu trees. There are several ways to get a two approximation for arbitrary k. And Gomori-Hu trees also exist for symmetric submodular functions or even divide and conquer. Several approaches give two approximation for min-sum symmetric submodular k partition, which also implies min-sum hypergraph k partition has a two approximation. And then for general submodular functions, you can get an order k approximation. This is Zhao, Nagamuchi, Ibaraki, and which was also improved by Okamoto, Fukunaga, and Nagamuchi. Yeah, both give some, they improve on the constant, but both are order k, which also implies order k for hypergraph KCut. And then very recently, like 2018, not very recent anymore, but you cannot beat the two factor for min-sum graph k partition. So 2 is the best and you can get type 2. So in a sense that also implies you can't get better than 2 for min-sum symmetric submodular k partition. So that is also 2 minus epsilon in approximable. So essentially min-sum symmetric submodular k partition, you can see approximability and approximability are tied. But the inapproximability is under the hardness of under densest k subgraph hardness. So it's not the P naught equals NP hardness, but it's a different assumption. And yeah, so all these once you have min-sum graph k partition is 2 minus epsilon approximable, the other cells also fill up. So you can see that you get tight results on these cells. You get 2 approximation and 2 minus epsilon approximation. So there's not much that one can do. And then for for hypergraph KCut, under densest k subgraph hardness, under densest k subgraph assumption, you can't get into the 1 over 12 minus epsilon approximation for this. So this is this was Chekuri and Lee's result. So in a sense, you can't hope for better than k approximation in that cell, which also implies you can't get better than k approximation for min-sum submodular k partition. So all these cells are pretty much tied. It seems very unlikely that we will be able to improve on these. You can see polynomial inapproximability in a sense. So there is not much open here in the min-sum version for arbitrary k. For min-max, turns out the reduction by Chekuri-Lee is in fact showing hardness of min-max hypergraph k partition. So this is also n to the 1 over 12 minus epsilon in approximable, which also implies that min-max symmetric submodular k partition has the same in approximability. And yeah, last year we managed to show that min-max graph k partition for arbitrary k is also NP hard, which also implies the other two problems are NP hard. And for min-max symmetric submodular k partition, you can get a 2k approximation, which is an order k approximation. So yeah, so that cell, there is again not much that you can do to improve. You can only get 2k approximation and there's n to the 1 over 12 in approximability. And for min-max graph k partition, you immediately get 2k approximation for all these. Okay. And so the only place where there is some scope for improvement or some scope to understand is this one, min-max graph k partition. We don't know the inapproximability here. We have this inapproximability result for min-max hypergraph k partition, but we don't, that does not generalize to min-max graph k partition, so we don't quite know. So this is the only that red question mark is the only place where there may be some room for improvement. Otherwise, there is really nothing that one can, at least, yeah, I don't see much any more interesting questions here. And if you're interested in FPT, again, I'll tell you there is, in fact, FPT, anything about hypergraphs, FPT is impossible when parameterized by K and the solution size. And for graphs, parameterized by K is W1 hard, and parameterized by K and solution size is poly-time. Parameterized by K, there are fixed parameter approximation schemes. Yeah, so that's the status for FPT. I don't have a slide for that, but yeah, there I think everything is pretty much resolved. Improving the dependence on in the FPT runtime, that may be still open, yeah, for graphs. But for hypergraphs and general submodular functions, things are hard there.
So seems like we don't have any more questions. So maybe we can stop the recording and we can have an informal chat if that's okay with you, Karthik.
Yeah, that sounds good.
So yeah, so let's first thank Professor Karthik, and also we'll have the second part next week, same time. So